Okay, so let us recall the last point of the previous video. We were here. F is a field, K is an extension of F, and A is an element in K. For these things, we defined the subfield obtained by adjoining A to F, or the smallest subfield of K containing both F and A, which we denote by this symbol, and the definition is this. Where FA is defined to be an intersection like this, where M is the collection of all subfields of K containing both F and A. We have seen that this FA actually is itself a subfield of K which contains both F and A, and as such the name we have given to it, namely the smallest subfield containing both F and A, is justified. Now this definition and these facts about FA are all external, in the sense that okay, FA is the smallest subfield of K containing both F and A, but we don't yet know how the elements in FA look like in terms of F and A. So that will, if we are able to say something like about that, then that description will be an internal description of FA, and that's what we are going to see now. Consider the following set. We denote it by U. Beta 1a and so on up to beta m a to the power m, such that n and m are non-negative integers the alpha i's and beta j's all belong to F. And the denominator in this expression, of course, is non-zero. That condition should also be there, otherwise this expression won't make sense necessarily. So what is U? U is the set whose elements are quotients of polynomials in A, where the coefficients are coming from F. Okay, now the first fact about U is that U is a subfield of K. Clearly this is, after all, I mean, whatever these elements are, after all they are going to be elements in K, because all we are using are elements of F and A in forming these quotients. So all of these are elements in K, so U is a subset of K. It can be proved that U is a subfield of K. This you have to do. It's not very difficult. First you show that this is a better way of proving it. You consider another set which look like this. Where n is a non-negative integer and alpha I belongs to F for I lying between 0 and n, or rather for I varying from 0 to n. You prove that this set T is a subring of K. You first show this, which would be a routine task. Okay, once you prove that T is a subring of K, next you observe this, that U is nothing but quotients of oh, we cannot use A because A is our special element, U by V, where U and V are in T and V is not equal to 0. Then with this observation and the fact that T is a subring of K, it will then be an easy matter to prove that U is a subfield of K. So that way you can do it. So I leave that to you. It can be proved that U is a subfield of K. Since U contains both F and A. How does U contain F? This just means U containing capital F means every field element is also in U. To see that, you just choose any field element, say alpha naught, and you choose n and m both to be 0 and you choose beta naught to be 1. Then this element becomes alpha naught. So alpha naught is in U. That means every element of capital F is in U. And it also contains A. To see that, you choose this denominator again to be 1, and in the numerator you take all the alpha i's 0 except alpha 1, which is 1. So the element you get is A. So that's how U also contains A as an element. So U is now a subfield of K that contains both F and A. So U belongs to M, and as such U will contain the smallest subfield that contains both F and A, that is FA. So we have this. But if K prime is any subfield of K containing both F and A, then U is contained in K prime. Why? You see, if K prime is some subfield of K containing both F and A, since K prime contains both F and A, so these expressions, first of all the expressions, the polynomials in A with coefficients from F, these expressions will all be inside K prime, because K prime contains all these alpha i's and K prime also contains A. So such expressions, polynomials in A, will be elements of K prime. But K prime is not just a ring, it's a subfield of K. So after that, after observing that all the elements in T are in K prime, possible quotients of such elements in T will also be in K prime, because it's a subfield. In other words, every element of U will be contained in K prime. So that's why U is contained in K prime. So that means U is contained in every element of M. So U would also be contained in their intersection, which is nothing but FA. This implies U is contained in FA. Now you combine these two inclusions. Hence, U is equal to FA. This way we have found the general structure of elements in FA in terms of the field F and the element A. So elements in FA in general look like this. So this is an internal description of the field obtained by adjoining A to F, or in other words, the smallest subfield of K containing both F and A. Okay, now we see what an element in K being algebraic over F has to do with finite extensions. So we are now going to link algebraicity of A over F and finiteness of the extension FA over F in this theorem. The element A belonging to K is algebraic over F if and only if the subfield obtained by adjoining A to F is a finite extension of F. Let us now prove this result. Oh, I am writing solution. Proof. So there are two directions we have to prove. First, assume that FA is a finite extension of F. This means the degree of FA over F is finite. Let M be the degree of FA over f. So our assumption means that m is a positive integer. Now we are now going to consider m plus 1. We cannot say immediately m plus 1 elements, but m plus 1 symbols. Now consider the elements 1, a square and so on up to a to the power n in K. Don't write in F, okay, because all we know is that A is an element of K. A may not be in F, so don't make that mistake. So these are elements in K. Now we don't really know at this stage whether these elements are distinct or not. They may not be distinct. There may be repetitions in this list. If these elements are not distinct, say, then there exist integers I and j satisfying these inequalities such that a to the power I is equal to a to the power j. Then A satisfies the non-zero polynomial x to the power j minus x to the power I over f. It's a non-zero polynomial because j and I are distinct and the coefficients are also not 0, they are 1. But then since A satisfies such a polynomial, so by the definition of algebraicity, A is algebraic over f. Oh, but okay. Should I write the conclusion in this case separately and then again? Okay, let us write. But then A is algebraic because we have to also consider the case where the elements, these elements are distinct. Algebraic over f. Now assume that these elements are distinct. Now these are elements in K that now because of the distinctness they are m plus 1 in number. From a to the power m there are m elements and this extra element and together they are m plus 1 elements. Since there are m plus 1 elements, these are linearly dependent over f. The reason is that since m is the degree of fa over f, so that means m is the dimension of the vector space fa over f. So any set of m plus 1 elements will be linearly dependent. It's more than the dimension. Thus, there exist elements, say alpha naught, alpha 1, etc., alpha m belonging to f, not all 0, such that this linear combination alpha 1a plus alpha 2a square alpha m a to the power m is equal to 0. Okay, so this is coming from linear dependence of these elements in k over f. But then A satisfies the non-zero polynomial alpha naught plus alpha 1 x plus alpha 2 x square etc. plus alpha m x to the power m in fx. Why is this polynomial non-zero? Because not all the alphas are 0, so not all the coefficients are 0. But this implies A is algebraic over f. So in any case we have shown that if fa is a finite extension of f, then small a is algebraic over f. So one half of the result has been proved. Next we prove the converse. Assume that a is algebraic over f. That means by definition A satisfies a non-zero polynomial over f. Then there exists a non-zero polynomial over f that A satisfies. So that means if we look at the set of all non-zero polynomials over f, in other words, if we look at this set, then there are polynomials in this set that A satisfies, and since these are non-zero polynomials, so each such polynomial has a degree. Okay, only the zero polynomial does not have a degree. I mean, we did not bother to define it to be either -1 or minus infinity. But in our case, uh, since these polynomials are non-zero, they have degrees, and those degrees are non-negative integers. That is the point. So that means obviously there will also be a polynomial, a non-zero polynomial which A satisfies and whose degree is the minimum possible by the well ordering principle. So that's why let Px be a non-zero polynomial over F such that Px is satisfied by A, that means Pa is 0 and degree of Px is minimum. What this means is this: if we consider a polynomial, a non-zero polynomial over F, any non-zero polynomial whose degree is less than the degree of Px, then it will not be satisfied by A. Okay, so that is the nature of the minimality of this degree. Okay. Now our aim is to now prove that this Px is actually an irreducible polynomial over F. To prove that, we assume that Px has a factorization over F like this: Px equal to Fx times Gx, where both Fx and Gx are polynomials over F. Okay. Then, since A satisfies P, so Pa is 0, but it turns out that this Pa actually, because of this, is also equal to Fa Ga. Exactly why this is true, that we will see in exercise 1 at the end of this section. See exercise 1. Okay, so now look at this equation: 0 equal to Fa times Ga. Since Fa and Ga are elements in K and K is a field, so product of two field elements is 0, so at least one of them should be 0. So either Fa is 0 or Ga is 0, or of course both are 0. Assume, without loss of generality, that Fa is equal to 0. Okay. Since Fx, the polynomial Fx itself is non-zero, why is the polynomial fx non-zero? It's because if fx is 0, then px would become 0, contradicting our choice of px as a non-zero polynomial over f. So fx itself is a non-zero polynomial. So that means it will also have its own degree. Since fx is not equal to 0, okay, so now what? Let us see what we have. F is a non-zero polynomial over capital F which A satisfies, and Px is a non-zero polynomial over capital F which A satisfies, but also degree of Px is minimal. So that means degree of fx will be greater than or equal to degree of Px. The minimal nature of degree of Px implies that degree of fx is greater than or equal to degree of Px. But since Px is fx times gx, from a previous result we know that this degree will be degree of fx plus degree of gx. But then this is equal to degree of fx plus degree of gx, which implies, oh, by the way, since fx is non-zero, the reason for which fx is non-zero, a similar reason also tells us that gx is non-zero. That's why we are able to write degree of gx, because if gx is 0, then again px becomes 0, which is not possible. So which implies, what do we have now? Degree of fx is greater than or equal to degree of fx plus degree of gx. So this implies 0 is greater than or equal to degree of gx. But since gx is a non-zero polynomial, its degree is a non-negative integer. But this one says that, this inequality says that the degree is non-positive also. So the only possibility is this, the only choice. Thus, degree of gx is equal to 0. That is, gx is a non-zero constant polynomial. What does this conclusion say about Px? We considered Px to be a product like this, where fx and gx are any polynomials over f, are some polynomials over f. And we have now proved that one of them has to be a non-zero constant polynomial, which we know is a unit in fx. So this just shows that Px has no non-trivial factorization over capital F, or in other words, that Px is an irreducible polynomial. Hence, Px is irreducible over f. Now next we are going to define a special type of mapping. Define a mapping psi from the ring fx, polynomial ring, into the field fa obtained by adjoining a to f by, what is the rule? The rule is this: any element hx is mapped by psi onto the field element ha. Because if we evaluate the polynomial h at a, then this is going to be an element in fa, because after all, you see, if h is a polynomial like this, say some gamma naught plus gamma 1x etc. plus gamma k x to the power k, where the gammas are f elements, are elements coming from the field f, then ha is this, which after all is an element in k, in fact not just k, it's an element in fa, because it has been formed by using some elements of f and powers of a. Okay, so this function is well defined, and in fact one can prove that it's not just a well defined function, it's a homomorphism of the ring fx into the field fa, and that also we will see in exercise 1. We can prove that is a homomorphism of the ring fx. We are writing like this because we want to stress the fact that it's a ring homomorphism into the field fa. And what is the kernel of this homomorphism? By definition, the kernel V of psi is the set of those elements in fx which give us the zero element in fa, that is hx belonging to fx, which when you evaluate at a you get 0. Loosely speaking, this kernel is the set of those polynomials over f which a satisfies. Okay, now recall that since this is a ring homomorphism, this kernel V is an ideal of fx. But we have already proved before in our section on polynomial rings that fx is a Euclidean ring. So this ideal will be a principal ideal, and in fact the element or an element that will generate this ideal will be an element having the minimum d value. But since we are in a polynomial ring, we know that the d function is degree. So phi will be generated by a polynomial that a satisfies and which has minimum degree. Px is such a polynomial. Okay, so V will satisfy, V will be generated by Px, and we are saying these things because in the very first result in the theory of Euclidean rings, where we proved that in a Euclidean ring every ideal is a principal ideal. We in fact did the proof this way. You consider R to be a Euclidean ring and you take I to be any ideal in R, then you consider, which of course is different from the zero ideal. Then in I you consider an element A that has the smallest d value. dA is minimum. Such an A, then we saw, generates I. Similarly, here Px, of course it belongs to V, because P is a polynomial over F that A satisfies. P of A is equal to 0. I mean, we don't see it here, but we already saw this. And P has minimum d value, minimum degree. So Px will generate V, since PA, or rather Px belongs to V and degree of Px is minimum among the, or let us write like this, is and Px has the minimum possible degree among the non-zero elements of V. It follows from the theory of Euclidean rings, which appeared in which section? I forgot. Do I have it here? Section 3.9 follows from section 3.9 that V is generated by Px. Now the fact that Px is irreducible over F will tell us something more about V, namely that V is a maximal ideal. Since Px is irreducible over F, V is a maximal ideal, and so the quotient of Fx by V, which we can of course form since V is an ideal of Fx, is a field, because when you form a quotient of a ring by a maximal ideal, you get a field. Okay, now what do we know from our homomorphism theorems, or first isomorphism theorem? Psi is a ring homomorphism from Fx into Fa, and its kernel is V, and we have found that fx by V is a field, and this field we know from our isomorphism theorem is isomorphic to a subfield of Fa. Subfield because this itself is a field. Now, instead of mentioning that this is a field, let us first write this. Now, as a ring, fx by V is isomorphic to a subring. Let us give that a name also. What should we call it? Let us call that L. A subring L of Fa. Since this is a field, so L also has to be a field. So that means L is a subfield of Fa. That means L is contained in Fa, and as such L is also a subfield of the largest field in discussion, that is K. Now, for any alpha in F, we have alpha psi. What is the meaning of alpha psi? You see, the inputs in the function psi are polynomials over F. So we can think of alpha as a constant polynomial over F, which actually it is. So if you calculate the psi image of alpha, then by definition it's evaluating alpha at A, but since alpha is a constant polynomial, this is equal to alpha. Okay. So alpha belongs to L. Note that L is actually the image of this function psi in Fa. So that means alpha belongs to L, that is F is contained in L. Also, what happens when we calculate the psi image of x, because x is also a polynomial over F, we get nothing but A. Thus, A belongs to L. So L has now become a subfield of Fa and hence a subfield of K that contains both F and A. So L is a subfield of K containing both F and A. And hence the smallest such subfield will be contained in L. Now you look at these two inclusions. One inclusion, of course, we haven't written explicitly. L is contained in Fa because after all it's a subring of Fa, but Fa is also contained in L. Thus, this which is isomorphic to L is equal to Fa. So we have shown that Fx by V is actually isomorphic to Fa. Now, the dimension of this as a vector space over F is, or rather I should write like this, can be shown to be the degree of the polynomial, that polynomial having minimum degree, and this we will see in exercise 2 at the end of this section. Hence, correspondingly, the dimension of Fa over F, which is nothing but the degree of Fa over F, is also equal to the degree of P of x. That is, Fa is a finite extension of F. So, Fa is a finite extension of F. Okay, so this is the only if part or the converse part. Namely, if A is algebraic over F, then Fa is a finite extension of F. Now we are going to redo the only if part in a slightly different manner, because you see, the only if part that we proved here, the converse part, we did not see any reason for why suddenly one has to consider such a Px of minimum degree, and then suddenly one has to define such a function psi, so that in the end everything falls in place and we get what we want. So let us take a more natural approach to the only if part and let us redo it. So again, so this is an alternative approach to the converse part. Again, assume that A is algebraic over F. Let Px belonging to Fx minus 0 be as before. That means Px is a non-zero polynomial that A satisfies and Px has minimum degree. But now we are going to do something else also to Px. Say Px originally looks like this: alpha naught plus alpha 1 x etc. plus some alpha n x to the power n. Okay, where since we are writing alpha n, there is no point in considering alpha n to be 0, because if alpha n is 0, we can as well not write that term at all. We have written till alpha n means we are assuming that alpha n is non-zero, and in fact the degree of px is n, say. Now if instead of considering px you consider this polynomial divided by alpha n, so that your new polynomial is this. Clearly this is also a polynomial that A satisfies, because after all this is nothing but px divided by alpha n, and p of A is 0, that is known to be 0. So note that this polynomial also has the same minimum degree n that px has. It is satisfied by A, but one more thing that can be said about this polynomial is that it's a monic polynomial, because the coefficient of the highest degree term is 1. Now there is a fact about this monic polynomial. You can have only one monic polynomial which has minimum degree, and so that it A satisfies it. Why? You see, suppose you have two different monic polynomials with that property. Say one of them is fx, which looks like this, x to the power n plus and you have another monic polynomial both are having the minimum possible degree, so that A satisfies such a polynomial, and both are satisfied by A. Then fx minus gx is also a polynomial that is satisfied by A. And what is fx minus gx? These two terms cancel each other, and we have a polynomial like this. Since fa and ga are both 0, so if we evaluate this difference at A, that will also be 0. So this is a polynomial that is also satisfied by A, and clearly its degree is not n. It is less than n, provided it has a degree. But then minimality of n is contradicted. So that's why this polynomial cannot have a degree. In other words, all the coefficients must be equal to 0. That is, all of these corresponding coefficients are equal, proving that fx and gx are equal. So if we consider a monic polynomial that has minimum degree that is satisfied by A, then there is only one such polynomial. It is unique. So we are not going to write these things. And it is called the minimal polynomial for A. We can consider Px to be monic in this case Px becomes unique. We have already seen why that is so. This Px is called the minimal polynomial of A over F. Okay. We are now actually going to write an expression for this polynomial. So that we can use it. Px equal to x to the power n plus alpha n minus 1 x to the power n minus 1 and so on, alpha 1 x plus alpha naught, where these are of course elements in the field F. Since, or let's write like this, from Pa equal to 0 we get A to the power n. So if we if we substitute A for x, a polynomial in A will be equal to 0, a monic polynomial in A. From that we can write A to the power n equal to minus alpha n minus 1, A to the power n minus 1, etc., minus alpha 1 A minus alpha naught. And this relation allows us to say some things about the higher powers of an. Note that A to the power n plus 1. What can we say about A to the power n plus 1? Of course, it's A to the power n times A, or for convenience, A times A to the power n. So this is equal to, if we multiply this expression by A, we get this. A square minus alpha naught A. In place of this A to the power n, we can again substitute this expression, which is a polynomial expression in A, where the highest power is A to the power n minus 1. So this is equal to minus alpha naught and so on. So we see that ultimately, after doing all the necessary calculations and after simplifying everything, again A to the power n plus 1 also is an expression, a polynomial expression where the highest power of A is A to the power n minus 1. In general, for any non-negative integer, k, a to the power n plus k is a linear combination of these elements, these powers of a. Okay, so that's what we can say from all these things. Okay, now consider a set T. It's actually that T that we were mentioning while showing, or rather saying, that capital U is a field. Beta naught plus beta, I need ink. Okay, so beta naught plus beta 1 a plus beta n minus, oh, it's not exactly that T that we were talking about, because that T consists of all polynomial expressions in A where any power of A is allowed. Here, however, we are going to consider only till n minus 1, where the betas of course are in F. Okay, so we are going to consider T. Clearly, T is closed under addition, which one can almost see why that is the case. You add any two elements in T, you again get an element in T because of the structure of these elements. Also, from our discussion above, T is closed under multiplication. You multiply any two such elements, you get a linear combination of powers of A. In such a linear combination, if you get a power like a to the power n plus k, where k is a non-negative integer, that itself becomes a linear combination of this. So ultimately you end up with an expression that is again a linear combination of these elements, these powers of A, or that is again an element in T. So T is closed under addition as well as multiplication. In fact, T is closed under subtraction if we really think of it. So T is a subring of K. That's what we want to. So T is a subring of K. That's what we want to conclude. Now we are going to show that not only is T a subring of K, it's in fact a subfield of K. So for that, let U be a non-zero element in T. Say some element beta plus beta 1a etc. in T. We want to prove that U has an inverse. Of course, U has an inverse because you see the elements in T are after all elements in the field K. So U is a non-zero element in K, so its inverse is there in K, but we want to prove that its inverse is actually inside T itself. So for that, let Hx be this polynomial plus beta 1x etc. plus x to the power n minus 1 in Fx. Since U is not equal to 0 and U is equal to HA, we must have Px not dividing Hx in Fx. Why? If Px divides Hx, that is if Hx is a multiple of Px where the other factor is also coming from Fx, then obviously HA will be equal to 0 because then HA will be equal to PA times that other polynomial also evaluated at A, proving that U is 0, which contradicts the choice of U. So that's why Px cannot divide Hx. Since Px is irreducible, Px continues to be irreducible because we have already seen that we don't even have to consider a monic polynomial. If we consider a polynomial that A satisfies, which has minimum degree, then that minimality forces that polynomial to be irreducible. So in particular, this monic polynomial Px is also irreducible because after all it also has minimum degree. Since Px is irreducible, so Px is irreducible and it does not divide Hx. So the greatest common divisor of Px and Hx in Fx is 1. So they are relatively prime. Px and Hx are relatively prime in Fx. So 1 is equal to Px times Ax plus Hx times Bx for some Ax and Bx in Fx. Relative primality of Px and Hx implies that such a linear combination will be equal to 1, the constant polynomial 1. This implies, now if we evaluate this polynomial, that is the polynomial on both sides at A, we get this 1 equal to PAO, this A will we will confuse this A with that A. No? So let us take A prime and B prime. A prime A plus HA B prime A, and this is equal to PA is 0, HA is U, so this is equal to U times B prime A. Okay, thus U inverse is equal to B prime A. So that means the inverse of U in K, which we know exists because U is non-zero, is actually a polynomial expression in A. So what else do we need to make it fall inside T? Namely that this polynomial expression contains only powers of A up to A to the power n minus 1. If it has higher terms, then those higher terms can be reduced using that formula. A to the power n plus k is a linear combination of those powers from 1 to A to the power n minus 1. In this, any term having A to the power n plus k, where k is a non-negative integer, is a linear combination of these powers of A. Thus, B prime A is itself a linear combination of this, that is B prime A belongs to T. So we now can say that T is a field. Thus T is a subfield of K. But from the structure of the elements in T, we can also see two things immediately, namely that T contains F, because T contains all the beta nodes, and T also contains A, which you get by choosing all the betas 0 except beta 1, which is 1. Okay, so T is not just a subfield of K, it's a subfield of K that contains both F and A. Also, it is easy to see that T contains both F and A. So, FA is contained in T. Moreover, any subfield of K containing both F and A contains T, because the elements in T are after all linear combinations of powers of A with coefficients from F. So if a subfield of K contains both F and A, so such combinations will automatically be inside that subfield, proving that T is contained in that subfield. So T is contained in every subfield of K containing both F and A. So T is also contained in FA. Thus, T is equal to FA. Now, what is the advantage of going through all these things? Note that we have shown that FA, every element in FA, because of this equality, is a linear combination of these elements. So, clearly, as a vector space over F, these elements span FA. Therefore, FA is spanned by these elements over F. Which proves that FA is a finite dimensional vector space over F, or in other words, this degree is finite. So that's how again we have proved that FA is a finite extension of F. Note that but in fact we can continue this proof a little more and say instead of stopping here itself, and in fact this is less than or equal to n, because keep in mind there are n elements in this list, n powers of A. Now, if this degree is actually less than n, then A satisfies a polynomial over F whose degree is less than n. Why though? I don't get this point. No. What I have written doesn't make sense. That's not how we are going to conclude that this is actually equal to n. Let gamma 1, gamma naught, etc., gamma n minus 1 be elements in F such that plus gamma 1a n minus 1. If at least one gamma I is non-zero, if at least one of these gamma i's is non-zero, then a non-zero polynomial, or rather the non-zero polynomial, in fx whose degree, because it is non-zero, it will have a non-negative degree whose degree is less than n. Now, what is the problem with that? The problem is that we have considered px to be the minimal polynomial of a. So its degree, which according to us is n, I mean that's how we chose px, is the minimum possible degree of a polynomial which a satisfies and which also is non-zero. But that would contradict the minimality of degree of p of x, that is equal to n. So gamma I must be equal to 0 for all I varying from 0 to n minus 1. Thus, these powers of a not only span fa over f, but they are in fact linearly independent, are linearly independent over f, which shows that in fact they form a basis for fa over f, and as such the dimension, this dimension is actually equal to n. That's how we are getting that this degree is n. Now let us look at a definition which again defines an algebraic element, but algebraic element of a specific degree. The element a in k is said to be algebraic over f of degree n if a satisfies a polynomial over f of degree n, but no polynomial over f of smaller degree uh, but no non-zero polynomial. Non-zero, of course, is I mean, it's there since we are talking about degree. Non-zero polynomial over f of lower degree. So from both of our proofs of the only part or the converse part of the previous theorem, we see that we have proved something more than what was asked in the theorem. In the course of proving theorem 512, in each proof we gave we proved a somewhat sharper result. Which can be stated as another theorem 513. If A belonging to K is algebraic over f of degree n, we know what this means. It means that the minimal polynomial of for A is of degree n. Then the degree of the extension fa of f over f is exactly equal to n. That is, the dimension of fa as the vector space over f is precisely equal to n. Okay, now we are going to state and prove a theorem whose proof uses these results that we have proved now, and it says a lot about algebraic elements. So this is theorem 514. If A and B in K are algebraic over F, then these elements are also algebraic over F. Then the sum and difference of A and B, the product AB, and the quotient A by B, which of course can be considered only when B is non-zero, are all algebraic over F. So in other words, sum, difference, product, and quotients of algebraic elements over F are again algebraic elements over F. In other words, the elements of K that are algebraic over F form a subfield of K. Let us see the proof. It's not immediate how that is true, but let us see the proof. Assume that A is algebraic over F of degree m. It will be the minimal polynomial for A over F will have some degree, let that degree be m, and B be algebraic over F of degree n. Okay. Then by this theorem, the subfield T, which is nothing but Fa, is of degree m over F, because that's what it will be. The degree of Fa over F will be equal to m. Now B is algebraic over F of degree n, which means P satisfies some polynomial say we consider that polynomial to be fx. Some non-zero polynomial over F whose degree is n. That's what being algebraic over F of degree n means. Since fx is also a polynomial in that's not how we should write Tx minus 0. Why? You see, T is nothing but Fa, and we already know that F is contained in Fa. So the polynomial ring fx is contained in the polynomial ring fax, which is actually Tx. So our B satisfies a polynomial in Tx over T, which is of degree n. Now over T, fx may not be a minimal polynomial. for B. There may be polynomials of lower degree than n over t. Over f, of course, n is the lowest possible degree, but over t maybe there are other polynomials, and since we are trying to reduce the degree, so we will look for lower degree than n. B satisfies a polynomial over t of degree n. Thus, P is algebraic over t. Since we are saying the polynomial has a degree, this fx, and anyway we have shown here that fx is a non-zero polynomial. So B is satisfying a non-zero polynomial over t, which says that B is algebraic over t. But the degree of this polynomial is n. Maybe there is a lower degree polynomial that also be satisfied, or maybe this is the lowest possible degree. In any case, algebraic over f of degree at most n. Okay. Now, by our first theorem on finite extensions, the degree of okay, so what are we having here? Fa is a finite extension of f, because A is algebraic over f. And now additionally we are having the fact that B is algebraic over t. So this is TB is a finite extension of t, but t is Fa. So TB is a finite extension of Fa, and Fa is a finite extension of f. So from theorem 511, TB will be a finite extension of f, and in fact we will have this times now this we have seen is at most n. Oh, but for that we have to again mention theorem 513. So theorem 513 implies okay, so this is at most n. Have I taken m and n correctly? M is the degree of A over f. That means this one, and n, okay. This is less than or equal to n, and this is equal to n. So by theorem, what will this be? From here I want to say that B is algebraic over f of degree at most nm. Yes, again by theorem 513. Of degree at most nm. Thus, by theorem 512, TB is a finite extension of f. Now think of TB. TB is actually equal to this. T is FA. So FA, we know what FA is. FA is the smallest subfield of K containing both F and A. TB is the smallest subfield of K containing both FA and B. So in TB we have both A and B. Since TB contains both A and B, it also contains this AB and A divided by B if B is not equal to 0. Now we take only one of these elements, say A plus B. Since A plus B belongs to TB, the subfield obtained by adjoining A plus B to F, just like FA, you can consider FA plus B, is a subspace of TB over the field F. Why? Because you see, since A plus B is an element in TB, so TB is a subfield that contains A plus B. TB is a subfield of that original field K that contains A plus B. But we already know that TB contains F. So TB contains both A plus B and F. So TB contains this. And as such, this becomes a subspace of TB over F. Thus, the dimension of this subspace over F is definitely, from our results on finite dimensional vector spaces, is less than or equal to the dimension of TB over F, which itself is less than or equal to Nm. So, by theorem 512, A plus B is algebraic over F of degree at most n. Similarly, A minus B, AB and A divided by B are all algebraic over F of degree at most nm. So that's what we wanted to prove, and in this case also you see that we have proved something more than what we were asked to prove, namely that so in fact we mentioned that in a corollary. If A and B in K are algebraic over F of degree n and m respectively, then A plus minus B, AB and A divided by B if B is non-zero are algebraic over F of degree at most nm. Okay, they are algebraic, but we can further say something about the degree of their minimal polynomials. Each minimal polynomial for these elements will be of degree at most nm. In the proof of this theorem 514, we saw the extension TB, which is FA B. We usually denote it by a notation like this. By F A comma B. Okay, so it's an extension of first we extend F to FA, then we extend FA by adjoining B to FA of B. That is denoted by this. Similarly, one can consider F B comma A, which you can understand what it is. It is slightly different. F B comma A is the extension of F B by adjoining A to F B. one can prove, in fact we are going to prove this in the exercises, one can prove that these two things are actually equal. In general, we can consider an extension like this. For elements or any finite number of elements in the original extension, original field K. Next, there is another definition. The extension K is said to be algebraic over F, I should not say over F, is said to be algebraic. That is, K is called an algebraic extension of F. In fact, let us just mention the extension K of F, yeah, that way we can write, is said to be algebraic if every element of K is algebraic over F. We are now going to prove one final result about algebraic extensions, which is in spirit similar to our first result, Theorem 511. That is, a finite extension of a finite extension is a finite extension. This time we are going to prove that an algebraic extension of an algebraic extension is again an algebraic extension. So that is Theorem 515. If L is an algebraic extension of K and K is an algebraic extension of F, then L is an algebraic extension of F. Now before we prove this, let me put some more ink. Okay, so here our aim is to prove that every element in L is algebraic over F. So let U be any element in L. Now we already know that U is algebraic over K because L is an algebraic extension of K. Since U is algebraic over K, we have elements sigma 1, sigma 2, etc. up to sigma n in K, not all 0, such that sigma 1 u to the power n minus 1 should we take like this, or okay, we can, if we want, we can take like this also, but then we have to start with sigma n. That is, algebraicity of U over K implies U satisfies a non-zero polynomial over K. Since K is also given to be algebraic over F, that means every element of K is algebraic over F. Okay, see, again I have written it over F. Extension is not over F. I mean, when we are saying it's algebraic, K is an algebraic extension of F. Several applications of Theorem 512 implies that this extension of F is a finite extension of F. In fact, let us give it a name also. M equal to this is a finite extension of F. So first of all, since sigma 1 belongs to K, so sigma 1 is algebraic over F, so you adjoin sigma 1 to F, you get a finite extension. Then sigma 2 is also algebraic over F, so you adjoin sigma 2 to O, but you cannot adjoin sigma 2 to F, but to F sigma 1. But okay, so how exactly are we applying 512 several times? First I apply, in the first application there is no problem. F sigma 1 is a finite extension of F. Then we apply again that to f sigma 1 and sigma 2. Okay, in here what are we getting actually? We are saying that several applications of theorem 5.1, not actually 5.1.2 but 5.1.3, implies that M is a finite extension of F. Am I missing something? How are we going to conclude that this is a finite extension of F? By theorem 5.1.1, the degree of this is this times the degree of this. Okay. I think I am missing something obvious. Actually, going through this much material at once, I think my brain is it has stopped working properly. So what I will do, I will just abruptly stop the video here. Only a little more is there, but we will continue in the next video. Okay, sorry for this situation, but I am not getting what is happening here. Why exactly this is finite, that I can't figure out. Let me give it a last try. Okay, by theorem 5.1.3, f sigma 1 of course is a finite extension of f. But then if I adjoin sigma 2 to f sigma 1, I still get a finite extension. No, it's not coming to me. So instead of pushing it further, after this we have, once we prove this, we have the last definition which says that a complex number is said to be algebraic if it is algebraic over the field of rational numbers, and complex numbers that are not algebraic are known as transcendental numbers. In fact, in the next section we will see that the number E, which we know from calculus or analysis, this real number is a transcendental number, and besides this there are many other transcendental numbers. In fact, there are more transcendental numbers than there are algebraic numbers. So all these things we will see in the next in the next video. Okay, so let me stop it here. If you have anything to say, you can write in the comment section, and you can mail me also here. You can send me queries or questions that you are trying to solve. There, of course, there is no guarantee that I will be able to solve all of them, because I am a human being, or rather Lucifer. I am not God. But we can try together. Okay, that is the point. So that will be all for today in field theory. So until the next video, this is me, Lucifer, from a mathematical room. Have a nice night.